Last lecture, I will discuss, well, we'll still have something to say about uniruled varieties, and I'll also talk a little bit about rationally connected varieties. Okay, so starting with uniruled varieties, so what we proved last time is that Fano varieties are uniruled. And what the first thing I would like to do today is to prove what I promised in the first class, which is that uniruledness implies that the Kollár dimension is negative in characteristic 0. So let me start by recalling some of the things that we have been seeing. So let me fix some notation. X will be a smooth projective variety over K on algebraically closed field. So we are interested in morphisms from curves to X. So right now, I want to consider only morphisms from P1 to X, but sometimes we fix some extra structure. So I will fix Z in P1, some closed subscheme, and a morphism H from Z to X. And I want to study morphisms F from P1 to X that extend the given morphism H. So as we saw last time, there is a scheme that parameterizes such morphism. So M morphisms from P1 to X extending H is a scheme parameterizing such morphisms. So let me recall that this scheme comes with a universal morphism. So we have an evaluation map from the space of morphisms cross P1 to X, which sends a point corresponding to a morphism F and T to F of T. And what we did in the first class is to give a description of this space in a neighborhood of a point. So let me restate some of the properties. So first, the tangents, if I fix a morphism F, then the tangent space at F of the space of morphisms is isomorphic to the space of global sections of the pullback of the tangent bundle of X twisted by the ideal sheaf of Z. We also saw that if, so this is the tangent space and the obstruction comes from the H1. So if the H1 of this vector bundle vanishes, then the space of morphisms is smooth at that point. We also had a lower bound for this, the dimension of the space of morphisms, but we will not need it today. So the third thing that we'll need today is in fact a description of the tangent map to this morphism. So the tangent map to the evaluation morphism at the point corresponding to Ft. So what is that? So this is a space goes from the tangent space of the space of morphisms, which by the first statement is just the H naught of P1 pullback tangent bundle twisted by the ideal sheaf of Z cross the tangent space at P1 to T, and this goes to the tangent space at F of T to X, and this is given by, so if I start with a global section here, alpha, and a tangent vector V, then the image will be, well, we evaluate alpha at the point T, and we add the derivative of F at T applied to V. Okay. So let's see what that means. So let's see what these conditions mean in the case when we have P1. So when we have P1, we know that the pullback of the tangent bundle of X, this will be written as a sum of line bundles. For some integers AI, it will be written like this. So for instance, if we want the space of morphisms from P1 to X to be smooth, what we want is that this H1 vanishes. But then we see that the H1, the pullback, the tangent bundle vanishes precisely if all the AIs are greater or equal than -1. So this will be one important thing. Moreover, we will study. We will want to investigate the dimension of the image of this map. Now, the dimension of the image of this map, at least in characteristic 0, will be precisely the rank of the derivative at the general point. So it will be important to understand when this sheaf is generated by global sections. So for instance, we see that the sheaf pullback of the tangent bundle is generated by global sections. If and only if all the AIs are greater or equal than 0. And notice that that is equivalent to saying that this sheaf is generated at a single point. Then we will also want to understand the same question for, say, the ideal sheaf of a point. In P1. So this is exactly the pullback of the tangent bundle twisted by -1. And this is generated by global sections if and only if all the AIs are at least 1. And so on. So for P1s, these questions are very easy to answer. So let me note also that for this splitting here, if the F is non-constant, then we know that the tangent bundle of P1 injects into the pullback of the tangent bundle of X. And this is precisely a node shoe. So in general, if the map is non-constant, then at least one of the indices here is at least true. Okay, so these are generalities, and let's see what we can say. Let's see what we can say when this sheet is generated by global section. So let me make a definition. So we let F from P1 to X be a non-constant morphism. So we say that F is free, respectively very free, if we can write the pullback of the tangent bundle as a sum of line bundles with all the AIs greater or equal to 0, and for very free we require that they are all greater or equal than 1. So before I give any precise statement, let's intuitively try to understand what a free and very free curve mean. So intuitively, a free curve or a free morphism can be deformed in any given direction. So let me try to make this a bit more precise. So let's suppose that we have a free curve C. And now let's assume that you give me at some point P, let's say the image of a point 0. Let's assume that you give me some tangent direction at this point P. So let me call it VP. So this is a tangent vector at P. And we can identify this with the fiber of the pullback of the tangent bundle at 0. Now, because this sheet, the pullback of the tangent bundle, is generated by global sections, I can find a global section whose restriction at this point is precisely VP. So since F pullback of Tx is generated by global sections, there exists an alpha global section of the pullback of the tangent bundle whose restriction to 0 is precisely VP. But now, notice that if the morphism is free, then the H1 vanishes And so this tangent direction, so this is precisely, recall that this is, we identified this with the tangent space at F of this space of morphisms from P1 to X. So because the H0 is, the H1 is 0, this space is smooth at that point, so this tangent vector, in fact, is a tangent to some curve on it. So since the H1, P1 of the pullback, the tangent bundle is 0, we can find a curve V through, say, V0. The space of morphisms from P1 to X, such that the tangent can find a smooth curve, in fact. Not necessarily proper, but a smooth curve. Such that the tangent bundle, the tangent space at P, is precisely generated by this alpha, this alpha. But what we are saying here is, so what we get here is a family of morphisms parametrized by B, so FB in B. So we get a family of morphisms such that when you look at the image of the point 0 and make it go to 0, the tangent direction that you get is exactly VP. So we get a family of morphisms such that D FB of 0 dB at B equals to B0 is precisely the given morphism VP. So given any point in the curve in any tangent direction, we can find the deformation of this curve that moves this point in this given direction. So this is the intuition. That's why we call them free curves. So maybe I want to keep this. So similarly, if you play the same argument, you see that a very free curve can be moved in any direction while you keep one given point fixed. So in order to make this precise, let me state a proposition that will make these intuitive statements into a precise statement. So proposition. So we fix X, the smooth projective variety, over K, an algebraically closed field. So first, if F from P1 to X is free, well, in this case, we already know that the space of morphisms is smooth at F, so it is contained in a unique irreducible component, and M is the irreducible component of the space of morphisms from P1 to X containing F. Then the corresponding universal morphism F from M cross P1 to X is dominant. And this is precisely saying that X is uniruled. And second, well, this will be a sort of converse of 1, but that only works in characteristic 0. So conversely, assume that the characteristic of the base field is 0. Then if I have Z is say an irreducible subvariety of the space of morphisms from P1 to X, is such that the corresponding universal morphism is dominant, well, and that says exactly that. This is equivalent to saying that X is uniruled, the existence of such a reducible subvariety. Then, for a general morphism F parametrized by Z, F is free. So the proof is very easy. It's basically look at the description of the derivative map. So proof so this is just to look at the derivative map. So in general, what do we have? So to say that, so if F from M, so F, so the first assumption is that I start with a free morphism. So F is free is exactly saying that the pullback of the tangent bundle is globally generated. But see, the image of the derivative map by this description here corresponds exactly at one point to the tangent vectors at this point. So the evaluations of these sections. Now, since this is globally generated, this is exactly saying that the Av at the point F and any point T in P1 is surjective. And this, of course, implies that F from M P1 to X is dominant. Now conversely, if the characteristic of the base field is 0, and we have F from Z to P1, Z cross P1 to X is dominant, then by generic smoothness, the derivative will be surjective at the general point. But then you just have to go back here to conclude that F is free for general F in Z. Just again by looking at the description of the evaluation map. So this proves the result. And notice that this gives us, what this is telling us, that this gives us a criterion characterization of uniruled varieties in characteristic 0. So this is saying that this gives us the following equivalence. If the characteristic of the base field is 0, then X is uniruled if and only if X contains a free curve, but now notice, so a free curve is a curve for which, so again, this is a curve for which the pullback of the tangent bundle is a sum of AIs with all the AIs greater or equal than 0. Now we can apply semi-continuity to observe that being free is an open condition. And so by semi-continuity, we get that X contains a free curve through a general point. So this is because being free, as well as very free, is an open condition. Okay, so this is a very nice characterization of uniruled varieties in characteristic 0 that definitely fails in positive characteristic. Well, I guess we can just okay, now let's prove some nice corollaries of this proposition. So corollary 1. This is what I promised in the first class. So we assume here that the characteristic of the base field is 0. then X uniruled implies that the Kollár dimension of X is negative. And let me recall what this means, i.e., this is just saying that for every positive integer m, the h naught of x, omega x to the power m, is 0. It does not have forms, non-zero global forms. Okay, so let's see how we prove this. So by this, so X is uniruled in characteristic 0. By this remark, says that it's equivalent to saying that there exists a dense open subset X naught in X such that every point of X naught lies in a free curve, in a free rational curve. So if we fix such free curve F from P1 to X, free curve, free morphism, what we have is the following. Well, by definition, the pullback of the tangent bundle is isomorphic with sum of line bundles of non-negative degree. So all the AIs are greater or equal than 0. And moreover, because the morphism is non-constant, some AJ will be at least 2. And now if I compute then who is the pullback of the omega x to the power m, this will be OP1 of minus of m times minus sum of the AIs. And this is negative, strictly negative. So what we see is the following. If I start with a section alpha of this vector bundle, so of this line bundle, so we start with a non-zero global form. Then I can restrict it to a curve, or in other words, I can pull it back by F, and this will be a global section of P1 pull back omega x m. But this space here, because this is negative, this line bundle does not have global section. So this is 0. This form is identically 0. Now this holds for any free curve. Now I have a dense open subset that is swept out by free curves. So what I conclude, so this says that omega restricted to x naught is identically 0, but then omega itself must be 0. So this shows that in characteristic 0, uniruledness implies negative Kollár dimension. And as I mentioned in my first class, the converse is one of the most important conjectures in this area, to characterize uniruledness by the negativity of the Kollár dimension. So let me restate this just to make the point. So big conjecture again, we assume the characteristic, the base field is 0, and then conjecturally, Kollár dimension of X being negative implies that X is uniruled. Okay, so next I want to give another corollary of the proposition. Again in characteristic 0. So again X will be a smooth projective variety over K, an algebraically closed field, characteristic 0. Then, in a sense, what this is saying is the following. So we will say that a very general point of X, for a very general point of X, every rational curve through this point is necessarily free. So let me make this precise. Then there exist countably many proper subvarieties Zi contained in X. Actually, they're properly contained in X, such that any rational curve meeting the complement of this variety, so meeting X minus the union of the Zi's, is free. So we call this set X free. If the field is uncountable, then this is a Zariski dense subset of X. If the field is countable, then really this does not say much, because this can be empty. Okay, so let's prove this. Okay, so we know that the space of morphisms from P1 to X has countably many components. So we let me give a name, Mi. I in N be the reducible components of the space of morphisms from P1 to X. And for each I will define Wi to be the closed subscheme of Mi parametrizing non-free morphisms. So this will be this set of morphisms in Mi that are not free. Now, as I said, being free is an open condition, so this is actually a closed subscheme of Mi. It could be the whole Mi. But now we notice the following. We notice that if we restrict the evaluation map to Wi cross P1, so this goes from Wi cross P1 to X, this restriction cannot be dominant, because if it were dominant, then for a general point in W, the corresponding morphism would be free. So by the proposition the image the closure of this image in X is not the whole X. And this is exactly the ZIs that I want. Then you check that this ZI will do the trick. Okay, so now maybe I should, before I go on, I should say that we have a similar proposition for very free morphism in place of free morphism. So proposition 2, I could state it like this. If I have, I start, maybe it's better if I rewrite this. So similarly, we have the following. So proposition 2. So again, X will be a smooth projective variety of an algebraically closed field. Then if I start with a very free morphism from P1 to X, sending, say, 0 to X, then the space of morphisms that send 0 to X, again, will be smooth because the corresponding H1 will vanish. And so there is a unique irreducible component containing this point, and M is the irreducible component of the space of morphisms from P1 to X that send 0 to X containing F. then the evaluation map is dominant. Then the F from M cross P1 to X is dominant. Let's just remark that this evaluation map will send M cross 0 to the point X. So this is exactly the intuitive idea that I showed, that a very free curve can be moved in any direction with one point fixed. And then conversely, assuming characteristic 0, then if I have Z, a closed subscheme of the space of morphism from P1 to X, that sends 0 to a fixed point X, and if such that the corresponding evaluation map is dominant, then for a general F parametrized by Z, F is very free. And the proof is exactly the same, just replacing the space of morphism with this space of morphism with fixed structure and the corresponding evaluation maps. Okay, I wanted to do some examples, but I guess I don't have much time. So let me leave this as an exercise to compute some examples. I'll just say what the result is. So first, the easiest case when X is Pn and L is a line. Then the restriction, we can use just the Euler sequence to conclude that the restriction of the tangent bundle to L will be like this. So you have this O2 here, which corresponds to the tangent bundle of the line, and then all the other factors are O1. So you see that this is very free, and indeed, if you fix a point in Pn and you let the line move, then it will sweep out the whole space. So this is indeed a very free curve. Now the next interesting example is concerns hypersurface. So we let X equals to XD in P n plus 1 be a hypersurface, a smooth hypersurface of degree D. So in order for this to contain line, we said that we saw that we have to take D to be less or equal than N. So what we saw is that the space for a general point actually for any point in X, we saw that the dimension of the space, we call it Gx, the space of lines on X containing the given X, so L in X, line through X. We computed the dimension of this space, or at least an estimate, when we saw that this has dimension at least n minus d. So in particular, under this hypothesis, we always have a line through a point. And in fact, it turns out that for a general point, we have equality here. And for a general line in X, then the restriction of the tangent bundle of X to L will be, well, there will be this old shoe, which is again the tangent direction to the line. Then we have n minus d copies of O1, and then, we have n minus d copies and then d minus 1. So we notice what we have here is that we fix a point, and then the space parametrizing the lines through this point will be Gx, which will have, for a general choice of X, will have dimension exactly n plus d, n minus d. And then we have here this cone, which are exactly the lines that are contained in X and pass through X. So we see that the dimension, so this will be the image of the evaluation map, and we see that it has dimension precisely equal to the rank of the derivative. So this is the positive part. So when you twist it by -1 to keep this point fixed, you get exactly, these directions will be kept non-negative. So it's a good to contemplate these examples a little bit. Okay, so now I would like to state, without proofs, some other important properties of free curves and very free curves. Okay, and these properties concern some different type of deformation than the ones that we have been considering. So far, we start with a curve, a map from P1 to X, and then we want to deform this map. But there are other important deformations. So for instance, if we are in P2, we can look at the following family of conics. Conics defined by x squared plus y squared equals t c squared. So this is a conic in P2, parametrized by t in, say, A1. And we see that for t equals 0, we have a union of two lines. And for t different than 0, then we have a smooth conic. So sometimes it is important to start with a reducible curve and be able to smooth it into, say, an irreducible, smooth, rational curve. So let me just state, well, actually, I'll just make a drawing of the properties of free and very free curves, which is the following. So let me just remark that in general, if you start in a situation like this with a smooth projective variety X and two curves meeting in one point, it's not always possible to smooth this reducible curve as we did here for the conics. However, so first property is, if these two curves are free, then it's possible to deform them into an irreducible and in fact free curve on X. So if you have C1 and C2 free curves on X that meet in some point, then we can find a smoothing of this curve. So we assume that they are free. And then the result says that we can smooth it into a free curve. And even more, it's possible to do that keeping one point fixed. Then one can deform C1 union C2 into a free curve keeping one point fixed. Oh, and then there are many similar properties. For instance, if one of these curves is very free, then the resulting curve will also be very free, and so on. So let me just state one more one more situation in this context, which is when you start with two free curves. So if C1 and C2 are very free curves, meeting at some point, then C1 union C2 can be deformed into a very free curve, keeping 2 points fixed. So one point, I choose one point in C1, the point in C2, and I am able to deform this reducible curve into a smooth, very free curve. So keeping x1 in C1 and x2 in C2 fixed. And now the third property that I want to explain is, in a sense, it's much more interesting. I mean, this is not hard to prove if you know a little bit of this type of deformation theory, but it's not complicated. Now, we may be in a different situation, that we may have irrational curves on some variety that it's actually not free. So suppose we are in X, and then we have a certain curve, let me call it C naught, not free. But for some reason, we would like to So it passes through certain points here. And for some reason, I would like to move this curve, keeping these points fixed. Now, if it's not free, then in principle, there is no reason why this can be done. But then we can use the free curves to do a very nice trick, which is the following. If I can find free curves, in fact, if I can find one, yes, in fact, this works even for non-rational, but we will only apply it to rational, because I have not defined the notion of freeness for non-rational curve, but it can be defined and the result will still be valid. But now suppose that I can find a free curve, say C1, that meets this non-free curve C0. Well, then I know that I can take a general deformation of C1 will be still free. And so in fact, once I have one curve, I can deform it and I can find it many free curves meeting C0. So I take C2 up to CK, free curves meeting C0. So if I take C big enough, so given, so let me write what I'm saying here. So given D greater or equal to than 0, if I take K big enough, and this big enough will depend on D, and attach these free rational curves to C0, then I can deform the whole union, keeping these points fixed. So if K is sufficiently big, and I have C1 up to CK free curves meeting C0, then the whole conc can be deformed into a free curve keeping any given D points fixed. So in the end, I deform this union, but keeping these points fixed. So this becomes an irreducible free rational curve. So when you have free curves in a smooth projective variety, they are very useful for doing deformation theory of curves on X. Okay, so these are the properties that I wanted to state, and now I will use them to describe finally rationally connected varieties. So finally, let's discuss a bit of rationally connected varieties. So unfortunately, I don't have time to say much about them, but this is an extremely important class of projective varieties. So remember that we were looking at uniruled variety, and then we considered, say, if we take an abelian variety A, and I cross it with P1, then this variety is uniruled, but all the rational curves will lie on fibers for the first projection. So studying rational curves will tell you something about X, but it won't tell you anything about A. So we are interested in the case when, by studying rational curves, we can say pretty much everything about X, or at least about some big open subset of X. So a natural condition to impose is that, say, any 2 points can be connected by a rational curve. Oh, but there's no reason why you should define rationally connected this way. We could also require that for general points x and y can be connected by, say, a chain of rational curves. So if you're able to say, to understand the rational curves, just connecting them by a chain will be enough to say something about these points. And so in principle, there's many possible definitions of rational connectedness, and an amazing fact that actually shows that this is an interesting class is that all these conditions that you can think of, in fact, are equivalent. So let me state a theorem. And for simplicity now, I will be always working over the complex numbers. I need characteristic 0 for generic smoothness. And in fact, I need another aspect of C, which is the fact that it's uncountable for the reasons that I explained before. So let me assume that X is a smooth projective variety defined over the complex numbers. Then the following conditions are equivalent. Well, so first, well, in fact, I could state many conditions, but let me just write it this way. I would just use 3 conditions. So the first, there exists a dense open subset x naught in X such that for any 2 points X and Y in X naught, then there is a chain of rational curves that connect them. So this is, in a sense, this is the weakest condition of rational connectivity that you can think of. So for 2 general points, there is a chain of rational curves connecting X and Y. Now the second condition is the following. Given any 2 points, not in an open subset, but any 2 points, I can connect them by a rational curve. And for any 2 points, X and Y, in X, there exists a rational curve containing X naught C such that both points are in C. And finally, so this third condition is similar to the characterization of uniruled varieties in terms of the existence of a free curve. So again, these conditions can be detected in a single curve, which is a very free curve. So X contains a very free curve. And then, once we prove this, then we can define rationally connected variety as being a variety that satisfies any of these conditions. So if these conditions are satisfied, then we say that X is rationally connected. So I want to sketch the proof of this theorem, but before I do so, let me just make a remark that that is the following. So we saw that for uniruled varieties, then you require that for a general point there is a rational curve. For rationally connected varieties, you require that through two general points there is a rational curve. So you could try to go further and make the following assumption that through any given 3 points there is a rational curve that connects them. And it turns out that if you try to do this, you will get nothing new. That in fact, so this is a remark, we stop at rationally connected. So being rationally connected, so if X is rationally connected, then given any finite set of points, you can find a rational curve through them. Then given any finite set of points, there exists a rational curve through them. And the proof is not much harder than what we are going to do now, but I'll just leave it as a remark. And in fact, you can even prescribe finitely many terms of the Taylor expansion of the curve at each of these points. So you have once you have one very free curve, you have rational curves pretty much with any finitely prescribed data. Okay, so now let me sketch the proof. So 2 implies 1 is obvious. So next I want to show that the existence of a very free curve implies 2, that any 2 points can be connected by a rational curve. So assume, so we want to prove that 3 implies 2. So we let f from P1 to x, say sending 0 to a point x0, be a very free curve. And as I said, the being very free is an open condition, so if necessary, I can deform this morphism to assume that x0 belongs to to x free. So we may assume that x0 belongs to x free. And we are given 2 points x and y in x. So we are given x and y in x. And we want to produce a rational curve connecting these 2 points. So here is the first step. So the first step we will connect this point x0 to x and to y. So what we can do is we can look at the reducible component of the space of morphism that keeps sends 0 to x0 containing f. So let M, the space of morphisms from P1 to x, sending 0 to x naught. Be the reducible component through f. So we know that f from m cross p1 to x is dominant. So the point x may not be in the image of this morphism, but because the morphism is dominant, it will be in the closure of the image. So we can find a sequence, or we can find a family of rational curves that all pass through x naught. So here is our x. So we can find a family of rational curves that pass through x naught, for which the closure of the family will contain the point x. But that means that maybe we cannot connect them by a single rational curve, but in the limit, these rational curves can only degenerate into a union of rational curves. So we can find we can produce a chain of rational curves connecting x naught and x. So let me redraw this chain here. So we have this chain of rational curves, and notice that because of the assumption that x naught is in x free, this first curve, let me call it c naught, is free. So I'll draw the free curves in green. And then the other curves, let me call these intersection points x1, x2, and so on, and this will be c1, c2, and so on. So the next step is the following. I will replace this chain that I obtained in step 1 by another chain that will, whose components will meet in the same points, but now all the CIs will be free. So the next step so step 2, replace each CI by CI prime, which is now a free rational curve that will still pass through xi and xi plus 1. So how do I do this? So now again, now I will use one of the properties that I have described. So the curve C1 may not be free, but once I have one free curve meeting it, I can produce other curves, other free curves that meet it, and then by taking sufficiently many free curves, I can deform their union keeping the points x1 and x2 fixed. So this will be C1 prime, and it will be free. So we can do this. using property 3. Okay, so now after this step, we are now in the following situation. We have x naught, and we have a chain of rational curves connecting x naught and x, but now each one of them is free. Free rational curves. Now I want to deform. What I would like to do now is obtain a very free curve through x naught and x. But we have to remember that we started our assumption, I have just erased the theorem, but our assumption 3 was that I have a very free curve through x. So this is now very free. And again, it's a matter of deformation theory that once you have a very free curve and a chain of free curves, they can be deformed. Let me call this C. They can be deformed into a very free curve, keeping x naught and x fixed. So step 3. We can deform C union C naught up to CK, C1 prime up to CK prime into a very free curve keeping x naught and x fixed. So we are in the following situation. We have our starting point x and our given point x naught and our given point x, and we have a very free curve through x naught and x. And I can do exactly the same for y. And performing the same steps, I produce a very free curve connecting x naught to y. But now, I guess this was what I stated as property 2. If I have 2 very free curves, then I am able to deform it into a very free curve, keeping 2 points fixed. So step 4 is to produce this very free curve. So step 4. Deform the 2 very free curves connecting x naught to x and y into a very free rational curve through x and y. So we proved more than the second condition. The second condition that just said that through any 2 points there is a rational curve. We actually show that once you start with one very free curve, given any 2 points, you can connect them by a very free rational curve. And now, let me just sketch the proof of the last implication. So now we want to prove that we can find a very free curve on X, assuming just that through 2 general points there is a chain of rational curves. So now we want to prove that 1 implies 3. So let me recall that 1 said that there exists a dense open subset X naught in X, such that for any 2 points x, y in X naught, there exists a chain of rational curves connecting them. And 3 said there exists a very free curve. And the proof is, in a sense, is very similar. So we start with a point x naught in x0 intersection f x free. Such a point exists because we are over the complex number, so we have a dense open subset and a dense subset. Now we know that given x in x naught, we can connect x to x naught by a chain of rational curves. And from this assumption, we know that the first curve is free. And now we do exactly the same thing we did in the last proof. We attached free curves and the form this union, keeping these 2 points fixed, to produce a chain of free curves connecting x naught and x. So as before, there exists a chain of free curves connecting x naught and x. And we did that for any point in x naught. Now we are over the complex, which is an uncountable field, and we found a curve connecting x naught with any point in this open subset. So there exists Then the next step is again to deform this union of free curves into we deform the union of the free curves into a single free curve. So we deform this chain into a single free curve. But we are not allowed to keep 2 points fixed. We only have free curves, you can only keep 1 point fixed. single, but we can, in any case, we can deform it to a single free curve, keeping x naught free, fixed. But then that means that we can find an irreducible component. There exists an irreducible component let me call it mx in the space of morphisms from P1 to x that sends 0 to x naught, with the property that this point x is in the closure of the evaluation map, such that x is in the closure of f mx cross P1. But now we can do this for any point x in a dense open subset. So since we are over an uncountable field, that means, so since we are over C, there exists an irreducible component M in the space of morphisms from P1 to x that sends 0 to x naught, such that the evaluation map from M cross P1 to x is dominant. But then, by proposition 2, we conclude that for general f from P1 to x is free, is very free, for general f in M. So this concludes the proof of the equivalence of the definition. So I hope that at least this result gives you a hint that this class of varieties is a very interesting class, but unfortunately I don't have more time to study them in more detail, so I will finish my course here.